All right, so we're talking about 14.7 in this video, and 14.7 and 14.8 both concern relatively the same idea. These two sections address optimization problems in multivariable functions. That's a major part of Calculus 1. Optimization problems looking for local extrema and absolute extrema for some function. You spend a lot of time talking about that, finding critical points, using your first and second derivative tests for finding local extrema and things like that. The work that we're going to do here is going to bear some resemblance to the stuff that we encounter in Calculus 1. So 14.7, the focus is on these maximum and minimum values. Local maxima, local minima, and absolute maximum and absolute minima as well. And then in 14.8, we're going to look at another way of optimizing functions given a particular constraint. We're going to talk about that, though, when we get there. So let's go ahead and start with some definitions, or a definition. We want to know what we're talking about when we refer to a local maximum or a local minimum when working with a function of two variables. So if you have a function of two variables, we say that this function has a local maximum at ab if f of xy is less than or equal to f of ab anytime xy is near ab. And the way we understand the word near is if there exists some disk around the point AB for which every xy within that disk satisfies this inequality. To kind of see why that would be the case, imagine sort of a dome shape like this. Okay? Something like this. In this dome shape, we can see that there is a clear, maximum point, meaning a highest point. If I were to, put some coordinate axes here and talk about this in the XYZ plane here, I could think of a small disk centered around that point in the XY plane. So that point right there is the point AB that we're talking about. And then if I graph just the points whose domain values live in this disk, notice it gives me like this little segment of that dome shape. That point right there is the highest point within that dome shape. Now this surface may do other things beyond that point. It may go all over the place. I don't know what this thing is that I'm drawing here. There may be points on the surface that are higher than this one, but at least within this small little disk, that point is the highest point. So that's kind of our justification for why we're describing this using a disk. In that case, we call the number f of ab. So whatever we get by plugging this into our function, giving us a z coordinate for this point, we call that z value, or that f of ab, a local maximum value. Similarly, if f of ab is the smallest point within that little disk, then we call, by the smallest, I mean the one with the smallest x value, or z values, the lowest point, we would call f a local minimum. This picture here gives you a sense of what local extrema look like compared to what we would call absolute extrema. So you see a bunch of like hilltops and valley bottoms of sorts in this surface. And for example, this little hilltop right here, we have a local maximum because I could put a little disk in the domain of this function such that when I plug that disk into my function, it gives me a little region with a little part of this surface where that local maximum is the highest point. However, that point is not the highest point in the entire part of the surface that we see because we have a taller mountaintop over here where the point reaches an absolute maximum. We have similar concepts for local minimum and absolute minimum values as well. This should look very similar to what we encounter in Calculus 1, except instead of looking at a curve, we're looking at a surface. All right? So we have this theorem that's going to help us characterize these particular points, where we can find, more specifically, local extrema, local maximum values, local minimum values. And this is very similar to something that we call Fermat's theorem in Calculus 1. We say f will have a local maximum or minimum at the point AB. Let me read that differently. If f has a local maximum or minimum at the point AB, and the first order partial derivatives of f exist there, then the partial derivative of x and the partial derivative of y at the point AB, will both equal 0. Compare this to Fermat's theorem in Calculus 1. If you're looking at a function that is differentiable at a particular value, and if the derivative at that value equals 0, then you have what's called a critical number. And it's at those numbers that local extrema may exist. We know that there's cases where they don't exist there, but that's where they would exist if the function is differentiable. So to prove this, we're going to define a function g of x, and we've seen this kind of thing before, a way of sort of turning a two-variable function into a single variable function by fixing one of the variables to a constant. F of x is going to equal, g of x will equal f of xb, and b is the y-coordinate of this point here. If f has a local maximum or minimum for that matter at AB, then g will have a local maximum or minimum at A. Okay, and it's easy enough to see why that's the case, because again, f of AB should be the largest, if we're talking about a maximum, value of f within a small disk surrounding this. So the largest possible value we can get out of this is if we plug A in. Okay, but Fermat's theorem, which I just mentioned a second ago, would imply that g prime of A is equal to 0. Okay, but what is g prime in this context? Well, again, g prime is the derivative of this function with respect to x. The derivative of this with respect to x looks like the partial derivative with respect to x. So to say that we're talking about g prime of A is the same thing as saying fx, the partial derivative of f with respect to x at AB, plugging A in for the x there. Following similar logic, if we apply Fermat's theorem to a different function where we define, in this case, capital G of y to be the function f of AY, now we're fixing x to the constant A, we could also show that fy of AB is equal to 0. So that's basically invoking Fermat's theorem from chapter 4 of this book, which is covered in Calculus 1, to prove this theorem, which is kind of like the analog in this higher dimensional case. Okay? Now, one thing that's worth noting is what happens when you have a point on a surface for which the partial derivative with respect to both x and y are equal to 0. If you substitute those values into the equation of a tangent plane, then those terms that have as coefficients fx and fy, those are going to go to 0, and the end result is going to come out to a plane that simply looks like z equals z naught. That is a horizontal plane, parallel to the xy plane. So what that means is that anywhere we have one of these local maximum and local minimum values that occur at one of these points where both the partial derivatives equal 0 at that point, then the tangent plane to that point will be a horizontal plane. Very similar to the corresponding concept in Calculus 1, where at critical points you have horizontal tangent lines. Right? I just drew that without showing you. So if I have a curve and I'm looking for those critical numbers where the function is differentiable, we get these horizontal tangents there. In this case, we get horizontal tangent planes. Okay, so it's kind of a similar idea. All right, so I want to find all of the critical points of this function. And again, what are we calling critical points? I don't think I stated it actually. When I refer to a critical point, it's similar to what we call critical points in Calculus 1. A critical point of a function of two variables, f of x, y, will be a point at which either of two things happens. Either both of the partial derivatives with respect to x and y exist and are equal to 0, both of them at that point, or if a partial derivative fails to exist, if either one of these fails to exist, then in either of those cases, the point AB at which that happens is called a critical point, or sometimes we call it a stationary point. Okay? So I want to find all of the critical points of this function right here. We'll talk about why this graph is here in a second. So what I need to do is find the partial with respect to x and the partial with respect to y of this function. What is fx? Well, it's a polynomial. We like those. The partial with respect to x would be 2x. That goes to 0. That becomes minus 2, and everything else goes to 0. 2x minus 2. And what about fy? What is the partial with respect to y? Well, it's going to look kind of similar. I get a 2y minus 6 for my partial with respect to y. Okay? Now, we want critical points, and critical points will be the points at which both of these partial derivatives are simultaneously equal to 0. Okay, so let's take a look at this first equation. It's only got one variable in it, so if I solved this for x, I'm going to get x equals 1. Okay, same idea here. If I solve this for y, I get y equals 3. So a critical point, there's only one critical point in this case, and it's the point 1, 3. Okay? Now, think about this in the context of the graph of this function, which is why I included this here. This is a quadratic function in 2 variables, and we know from chapter 12 that the graphs of the surfaces that we get from these functions are quadric surfaces. In this case, if I went through the work of graphing this, I'd find that this gives me a paraboloid. Particularly, or specifically, a paraboloid opening upward. And if you notice here, the vertex of this paraboloid is 1, 3, 4. I plug 1, 3 into my function, I would get 4 as my z value. And because that's a vertex of that parabola and because the paraboloid opens upward, that point is very clearly a local minimum for this function. It turns out it's also an absolute minimum, but more specifically, a local minimum. Okay? So we didn't ask you to verify whether this was a local max or a local min or neither. We just wanted to find if it was a critical point. But we can see that at this critical point, we do in fact have a local minimum just by looking at the graph. Okay, let's investigate another example. Both of these examples come out of the book. Normally I try not to do the same examples that appear in the book just to give you something else to practice. But I used these two because they both had images that I could use. And the images are really important for this concept. So I want to do the same thing here. I want to find all critical points of this function. What is fx in this case? It would be negative 2x. And what is fy? Positive 2y. If we want critical points, I look for anywhere that these partial derivatives fail to exist, but they don't fail to exist anywhere. Same thing happened in the previous example. So we're left looking for where they are equal to 0. In both cases, x and y will have to equal 0. So my critical point is the origin, 0, 0. Okay? Now, in this case, if we were to graph this is another quadratic in 2 variables, so its graph is going to be a quadric surface. And this particular quadric surface, if you remember from chapter 12, is a hyperbolic paraboloid. Looking at this hyperbolic paraboloid, the origin occurs right there. Okay, but is that a local maximum or a local minimum? It's neither, because any disk surrounding this point are going to have some points that are higher than it. If you kind of move along in the y direction, you can see that we have this upward opening parabola that acts as a trace there. Or if I move in the x direction, we'll find points that are lower than that point. That means if I move in the x direction, there's a downward opening parabola acting as the trace there. So no matter how small I make that disk surrounding the origin, I can always find points that are both higher and lower than the point that I have there at 0, 0, 0. That means that this is a critical point, but it's neither a maximum nor a minimum. And this is not unfamiliar territory because we get the same thing happening in Calculus 1. For example, if I look at the cubic function, y equals x cubed, for example, there is a critical point to this function at the origin, but that critical point is not a maximum nor a minimum because we have values that are smaller than it on the left and values that are larger than it to the right, even though a horizontal tangent occurs there. So that's the same concept, but in a higher dimension now. These types of points we call saddle points. The reason for that is because the hyperbolic paraboloid is sort of the standard example of where a saddle point occurs. And a hyperbolic paraboloid, this piece of it looks a little bit like a saddle that you would put on a horse. So that's where we get that name from. But saddle points will give you a critical point, or will be critical points at which neither a maximum nor a minimum occur. Okay, that's the term we're going to use for that. All right, so now we've talked about critical points, and we've looked at a couple of examples where we could determine whether the critical point was giving us a maximum, minimum, or a saddle point. But that required us to know what the graph of that surface looked like, because we had a visual that we could use to compare our critical point to the points surrounding it. Most of the time, you're not going to have a surface to look at. So we need to use something else. And that something in this section is going to be what we call the second derivatives test. Now you have a first and second derivative test in Calculus 1, and this is in a sense the higher dimensional analog, but it looks a lot different. So we need to take a little time to make sure we understand this. Let's suppose that you have this two variable function f of x, y, and let's suppose that it has second partial derivatives that are continuous on a disk with a center of AB. And then let's suppose that the partial of x with respect to, the partial with respect to x of AB and the partial with respect to y of AB are both equal to 0, which is to say that AB is a critical point of f, but specifically the type of critical point where the partial derivatives exist. Okay? So AB is a critical point, and then we're going to define this seemingly bizarre looking function, but we'll give some intuition, not some intuition, we'll give kind of a proof as to why we use this. We're going to define this thing D. We call it a discriminant. You may remember the word discriminant from algebra. When solving quadratic equations using the quadratic formula, the part of the quadratic formula that appears under the radical, b squared minus 4ac, we call that the discriminant. This is a kind of similar concept, so it gets the same name, but it's not the same creature. So this is the discriminant, d, or we might call it d of ab because it's going to be a function of ab. And it's equal to the second partial of f with respect to x both times, second partial of f with respect to y both times, both evaluated at ab, so I'm multiplying those, minus the mixed partial f of xy of ab squared. Okay, this quantity, whatever this thing comes out to, we call that the discriminant. Now, we break this down into three cases where we compare some values. If the discriminant is positive, and if the second partial with respect to x both times at AB is also positive, so if both of these quantities are positive, then f of AB will be a local minimum. If the discriminant is positive, so similar to case A, in both cases the discriminant is positive, but if the second partial with respect to x both times at AB is a negative number instead of a positive like it was here, then f of AB will be a local maximum in that case. If the discriminant is negative, then we don't care about what's happening with the second partial with respect to x both times. F of AB will be a saddle point, meaning it's not a local maximum nor a minimum. Okay? So this gives us all three cases in a test for how to come up with those. We're going to practice using the second derivatives test probably in the next video. I want to spend the rest of this video talking about how we prove this theorem. Now this theorem consists of three cases, so it would require three separate proofs, one for each case. I'm only going to prove part A. This proof comes straight out of your book. You can prove parts B and C using somewhat similar logic as this, and it's kind of lengthy, so we're not going to go through those. Let's instead just walk through the proof of part A. This is a difficult proof. It's a difficult one to get through, so I'm going to try and help make sense of all the steps here. Basically, what we're trying to do is we're trying to compute the discriminant of some function f of xy, and we're going to assume that this is true. We're going to assume that both the discriminant and the second partial with respect to x both times are positive. And then based on that assumption, we want to show that f of ab would be a local minimum as a consequence of that. So we have a function f, and what we're going to do is actually begin by working with a second order directional derivative. And I'll kind of explain what that means in a second. But our directional derivative will point in the direction of u, which is going to have components hk. This is the unit vector u. Okay, so from the work that we did in the previous section, we know that the directional derivative of f would equal fx times this first component of u, h, plus fy times the second component of u, which is k. Okay, now this, remember, this in its own right is a function of x and y. So as a function of x and y, we could also compute its directional derivative in the direction of u. Granted, it's a different function than f, we could still do that. So we're going to evaluate the directional derivative in the direction of u of the directional derivative in the direction of u of f, which would look like this. Okay? Now, how do we do that? Well, I would have to take the partial of this function with respect to x, multiply it by the first component of u. So that would look like this. H is the first component of u. And then I want to differentiate this partial derivative with respect to y and multiply that to the second component of u. Add those results. Okay, that's all fine and good. What happens if I take the derivative of this guy with respect to x? Well, remember, h and k are constants, so they're just kind of along for the ride here. And if I differentiate, I already have fx here. So differentiating with respect to x, again, gives me fxx. If I differentiate this guy with respect to x, I've already differentiated with respect to y, so I get fyx. And then the h and the k just stay put. Okay? So this little factor here turns into this guy. Similar steps here, differentiate this with respect to y, and I would get these two terms in parentheses. Okay? If I distribute the h and the k in, you're going to notice, first of all, I get fxxh squared from this term. I'm also going to get fyyk squared in this term. And then these two terms, I'm going to get fyxkh and fxyhk. Those I'm going to think of as like terms. And the reason I can do that is because fyx and fxy are equal to each other. Those are mixed partials, and Clairaut's theorem from section 14.3 would tell us that they are equal and can both be written simply as fxy. So combining those, I get 2fxyhk. I get this thing that looks kind of like a quadratic. Okay. Now, one thing that I can do with quadratics is I can complete the square. And by the way, if you're looking at this and you're thinking, why are we doing this? What's the point of these steps? I never would have thought to do this. It's not supposed to be obvious yet why we're doing this. We'll draw a result from it at the end of this proof. But the next step is to complete the square with this quadratic. And specifically, we're going to think of this as a quadratic in the variable h. So h squared, h, constant term. I'm thinking of k as a constant. Okay. If you remember how we complete the square, I'm going to jump to another page because your book just goes straight from here to here, and there's a lot of algebra that takes place between these two things. So focus for a second on this, and I'm going to show you some steps here. Let me move some stuff out of the way. Whoops. Okay. Trying to make that line up. All right. So the first thing I would do is factor the leading coefficient, which is fxx, out of the first two terms. And that would leave me with h squared plus 2fxy over fxxk. That's like my constant times h. Okay, I'm only factoring out of those first two terms, and I'm pushing the fyyk squared out of my parentheses there. Next thing I'm going to do is complete the square within these parentheses. And if you remember, you take half of this coefficient, and then you square it. So half of this is just going to get rid of the 2. Squaring it gives me fxy over fxxk all squared. Okay? Now, because we added something new in here, when you complete the square, you then have to subtract that corresponding term out here so that things would cancel out. But the term that I am putting in here is also being multiplied by this fxx. So taking this term, multiplying it by fxx, and subtracting that out here will compensate for the fact that I just introduced something new in parentheses here. Now we do some simplifying. We completed the square in here, so the result is going to factor down to a perfect square trinomial, where this term is just the square root of the constant term here. And then this guy, if I distribute my second power to fxy, fxx, and k, and then use this fxx to cancel one of those fxx's out, I get this term right here. Finally, I'm leaving this guy put, but I'm going to factor. I notice I have a factor of k squared showing up in each one of these, and I'm also going to factor out the fxx in the denominator here. So k squared over fxx is being factored out. That'll introduce a factor of xxx right here and leave me with minus fxy squared. This thing right here in parentheses is that discriminant that we talked about right there. Okay, so that's where it's coming from. But still, it's not clear why we're doing this. So let's push onward. Okay, now remember, we're proving case A of the second derivatives test, which means we're assuming that fxx at AB is positive and D, the discriminant at AB, is positive. What that means is that this coefficient here is positive and the stuff in parentheses here is also positive. Notice the only other parts of this expression is the stuff in parentheses here, which we are squaring, so that would have to be positive. And then this term out here, k squared over fxx, assuming fxx is positive means that this coefficient is also positive. So these two assumptions mean this whole entire thing is positive. Okay? Now, we're going to use a result that I can motivate, and I'm going to show you a little picture that I drew to kind of motivate it. But we're assuming that those second partial derivatives are continuous, which would also imply that D is continuous. And what that implies is this. If you have a function of two variables which determine some kind of a surface, right? And if f of AB is a positive number, and if that function is continuous, even if it's a very small positive number, that would imply that we could find a disk centered at AB in the domain, even if it's a very, very small disk, such that if we plug all of the points in that disk into our function, the resulting piece of our surface is still all above the xy plane, all still positive. Okay, that's a property of this being continuous because it means that none of these points can jump below the xy axis. Which would come from a break in our surface somehow. Okay, so hopefully you can kind of see intuitively why that's the case. But again, the idea is that we can put a disk, even if it's a very small disk, around the point AB in the xy plane, such that anytime you pick a point xy within that disk, which we're calling B, this function that we just evaluated will still be positive there. Okay? Now, why did we bother with a second derivative? Because this is not the original function, right? This is the second directional derivative. What this means for us is that if you were to intersect the surface that we get from f of xy, the original function, with a vertical plane in the same direction as that direction vector u, and I don't have a picture of this to show you, but we've seen something similar. So if we take our surface, put a plane through it, a vertical plane that's in the direction of u, then the result, the intersection between our surface and that plane, will be a space curve, which we call C. We've done this kind of thing before, so hopefully you should be able to picture that. And what this is saying is that if we're thinking of that as a plane curve now, the second derivative of that plane curve is positive. But do you remember what that means in the case of a plane curve? It would look, a positive second derivative means we're looking at a concave up curve, right? And that's concave up regardless of our choice of u. We chose u arbitrarily. So that means u could point any direction. So what kind of a curve, or what kind of a surface, rather, would have every single cross-section, every single plane that passes through that curve and the point AB, f of AB, What would it look like if that surface had concave down cross sections everywhere? Well, one such surface is something like, a paraboloid, right? Every cross section of this paraboloid, no matter how you take it, is concave down, right? Regardless of the direction at which that cross section goes through, provided it passes through this vertex. And that gives us this minimum down here. Okay, so the implication, if we want to use the definition, is that we can find a disk somewhere in our domain such that all of the points within that disk, when they get mapped onto the surface, will give us values that are greater than or equal to the z value at this low point right here. Okay, so it takes a little bit of time to talk through that proof. And I know it's probably a very difficult one to wrap your mind around. Don't worry about that if you're not understanding it. For our purposes, we just need to know how to use this test. I'm not going to test anybody on a proof of this magnitude. Okay, but that's all the time I have in this first video, so let's go ahead and move on to the next.